everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time, we're getting away from the basics, bulk properties of the sun, and we're going to talk about the sun's appearance. And what does it look like on its surface? So the sun, as you can see in this image, is in ultraviolet light or extreme ultraviolet light taken by the Solar Dynamics Observatory, which is an orbiting spacecraft, and with its arrays looking at 171 angstroms, which is approximately 10 times shorter than short visible wavelength light, or extreme ultraviolet. This is called extreme ultraviolet view of the sun. And we can see all sorts of very interesting features on the surface. We see over on the left-hand side some loopy type structures we'll call prominences. We have the prominences seen top down, which are the darker structures. We see like wisps going away from it. We call that the solar wind or the corona. And we also see hotspots, which are also active regions, which might contain sunspots, and usually do. They contain sunspots or other active things. And down close to the what we might say the surfaces, it kind of looks hairy, and those things might be called spicules. But let's see those more close up. Okay, so first things first, when you're done with this video and looking at it, you should be able to answer these questions and others. So do take a look at them and take a look and see if you can figure out them, and pause this thing and go back and look. This image of the sun was taken by Dr. Vishnu Reddy from University of Arizona. He was in Glendale, Wyoming with myself. I saw the total solar eclipse of 2017, and it was wonderful to go see. When the solar eclipse occurs, you get some amazing views of the sun. So why do we study the sun? There are numerous things, and we'll discuss these four in brief right now. We study the sun because there's a connection to our climate. Since it's the primary source of light and heat on Earth, everything that the sun does can influence how warm or hot the Earth is, and so it is the fundamental driver of all climate on Earth. When we know about what's happening on Earth, we can know about the history of the climate on Earth. If we know about the history of climate on Earth, we can understand, maybe potentially help us understand what might happen in the future on Earth. And as possibly, if we can understand short-term variations and their effect on the Earth's climate, that would be good too. All right, so first and foremost, we study the sun for that. Also, very practically, we study space weather. The sun, as you saw in that first image, emits what we call the solar wind, or particles are continually streaming off of it. Enormous amounts are continuously streaming off the sun and flowing out past into the interplanetary space. So this flow goes extraordinarily fast. It transmits it carries the sun's magnetic, or carries the print of the sun's magnetic field with it. And as it does so, it pumps the energy of the sun's magnetic field into the Earth's magnetic field, and that can influence satellite weather, communications, as well as satellites themselves. If it's an extraordinarily enough violent solar wind flow for whatever reason, then the Earth's then planes might need to be grounded, or if it's very violent geomagnetic storm, there might be power outages on Earth. So understanding the nature of space weather, or what the sun is doing to the space between in the environment between the planets, is incredibly important. Because without understanding it, we can have big problems, as we'll see later. Third, the sun is a star. And while the first two are really important in terms of very practical aspects for life on Earth, the third one is the nature of astronomy course, because the sun's a star, and since it's the nearest star, it allows us to understand details about other stars. So it's the metric by which we judge all other stars. And understanding how stars work, it starts with the sun. And we should be able to expect that if we go, or we're able to imagine ourselves next to another star, we start first with images and thinking pattern of the sun, and then try to imagine what it might be like different over there. And in fact, the sun as a star fundamentally tells us the nature of what stars are, and stars are the building blocks for galaxies. And then if we think about then galaxies are separate things we'll talk about later. So the physics of stars are very important, and how the sun behaves as a star is important. Finally, there are some very interesting questions in physics that come out of studying the sun, and you can, instead of building multi-billion-dollar large hadron colliders and so forth, you can say, well, I've got this idea about how the nature of physics works, and what is the nature of physics and how do particles interact on a nuclear level, you can say, well, the sun has to be doing nuclear fusion. And we'll see why in future lectures, that the sun produces the energy that we see by nuclear fusion. And as such, that nuclear fusion then gives us a test, a way to test our understanding of nuclear physics. So this is a really interesting way of talking about it. So in short, we have some important reasons to study the sun. So some other outstanding questions about the sun in terms of the future, which we might not actually get to, but we might in future times, is that how does the corona of the sun get heated? Nobody really knows. The complexity of which a solar flare arises, that's still an open question. It's mostly open, but the basics are understood. But how difficult it is to actually understand where a solar flare comes from, and we'll see what those are shortly. And sunspots come and go on the surface of the sun. That's incredibly important understanding because that links to climatic change apparently as well. And missing neutrinos is a particle physics question. Those are some principal questions. Some of these are answered to better than others, but these are some incredibly important questions about the sun. Now, everything that we're going to see about surface features on the sun is related to the magnetic field of the sun. The magnetic field of the sun is many thousands of times stronger than the Earth's magnetic field. And all of the things that we see on the surface of the sun, all of the surface properties are because the sun's magnetic field is not uniform and varies wildly and varies rapidly and can vary and changes with time. Unlike the Earth's magnetic field, which appears to be stagnant at the Earth's surface, it too is changing, but not with the dynamics of the sun. So the sun's magnetic field does everything. And one of the major satellites that's observing the sun today is called Solar Dynamics Observatory, and that's a NASA-based mission, and it has a series of telescopes and an ultraviolet exploration, and it also is able to detect motions on the surface of the sun, which allows it to image the magnetic field on the surface of the sun, and it takes images of the sun in various wavelengths, one in 10 wavelengths every 10 seconds, or one of those wavelengths every second. So the Solar Dynamics Observatory is designed to see very fast changes in order to understand what the entire disk of the sun is doing. Previous missions, such as Stereo and SOHO, didn't have the cadence or potentially even the size of Solar Dynamics Observatory. And SDO's goal is mostly to understand space weather. Its goal is to hopefully predict it. And in order to do that, they outfitted it with this little satellite with an ultraviolet explorer, ways to image the atmosphere of the sun in multiple ultraviolet wavelengths, as well as looking at looking at Doppler effect on the surface of the sun and being able to image the magnetic field of the sun through Zeeman splitting. So we're going to get some terminology, but the surface of the sun that we see in the disk in the sky, we call that the photosphere. And the photosphere is the surface of the sun from which the visible light appears to come. And that's defined as the location in the surface of the sun. We'll call it the surface, but it's not really a surface. The photosphere is about 100 kilometers thick, and it's still a gas. So even though it appears to have a sharp edge, the sun's size is so incredibly large compared to the thickness of the photosphere that it looks like a sharp edge. But the photosphere itself has edges that go out and appear to be darker, and it's called limb darkening, where the edge of the sun, or the limb, we should call the edge, the outer ring of the disk of the sun, we call the limb, appears to be darker. And that's because when you look towards the limb, you're looking at higher and higher elevation above the deeper portions of the sun. And as you go up in elevation from the deeper portions, it gets cooler in the photosphere. So therefore, since it's cooler, it is darker. So when we look in the center of the sun, or smack in the center of the disk, it looks brighter as well as yellower. And so that is because we're looking deeper into the into the sun, and so we see it where it's brightest. But the photosphere itself is where we get the visible light from the sun. Right, and the image that you're seeing here shows a progression of sunspots passing across the sun. And as we know, the sun rotates. So the photosphere is not a visible surface, and since it's about 100 kilometers thick compared to the sun's 700,000 kilometer radius, yes, you can't tell that it's an edge. So that's what we call limb darkening, and this image is definitely shows this. This image was an image taken of an active region, and we can see an enormous active region is seen by the SOHO satellite, or the solar, by another NASA mission, and that huge looping object that's in the middle. These are all sunspots, and these are active regions, especially the center one, which back in the end of October in 2003 launched an enormous solar flare. And that solar flare had some problems here on Earth, and it caused some issues down here on Earth. So let's look at the sunspots and what they are. And sunspots are really critical things because they look like blemishes on the surface, on the photosphere of the sun. They're cooler regions on the surface of the sun, and they have these very strange and interesting shapes. And this image was taken by Alan Friedman, who's a very interesting solar observer. All right, sunspots appear darker because they're slightly cooler than their surroundings. And so slightly cooler still is very hot. It was just 4,000 Kelvin versus about 6,000 Kelvin for the brighter areas of the sun. And we can see that that material in the sunspots appears to be moving, but it's not like it's a hole in the sun. It's not like there's no sun in the sunspot. No, it's just simply much cooler. So in the same sense that if you look into a fire at a campsite and you see that the coals look dark compared to the fire, you know that they're pretty hot and you wouldn't want to reach in there and grab them. It's just that they're cooler than the surrounding gases of the flame, and so therefore you wouldn't want to, they look darker. Now, again, the sun is not on fire. It is just so hot that it glows. And the reason the regions are darker is simply because they are cooler. And the central region is what we call the umbra. And the umbral region is a place of extraordinary magnetic field strength. And it can be, the sunspots themselves are where can be incredibly strong compared to surrounding the sun and compared to the Earth's global magnetic field. Sunspots themselves can last for a few days. Their appearance changes very frequently. They are dynamic objects. They change with time, and they can grow in size and then shrink in size. They can live for a few days or up to many weeks. And the outer portion we'll call the penumbra, and they always come in pairs. So sunspots come in two sets, where one set is magnetic north and the other set is magnetic south. So they come in pairs where one is in North Pole and one of us is South Pole. So we can imagine that underneath the photosphere, if you wish to imagine this, that there's some sort of magnetic, even think of those old bar magnets or those horseshoe magnets where one end is north and one end is south. And the magnetic field is poking out. And that's not a bad example because something like that is happening in the sun. Of course, there's no big old bar magnets inside the sun. It must be because of the flow of electrical charges deep inside the sun, where the magnetic field then is generated by this current flow, and that current flow then pops up through the surface. All right, also sunspots are enormously large. Most of them are larger than the Earth, and some of them can be even larger than Jupiter. So sunspots can be catastrophically large in size, and to see that they move and change and alter their appearance rapidly is really very interesting. All right, so this was another set of sunspots taken by Alan Friedman back in 2011, and we can see that some of these sunspots are really big. Remember that the Earth there's approximately 100 Earth diameters across the sun. So each of the sunspots that we're looking at, that were taken by Mr. Friedman, these sunspots are much larger than the entire Earth. These are huge sunspots. Okay, so you saw in the background there is kind of a structure, a honeycomb sort of structure, and they have a special name. Those are called granules. And granules are the visible top layer of the convection zone of the sun. So we can think of the sun as continuously burbling and boiling, if you wish, but it still is gases. So those are hot gases that are rising, and when they're very hot, they glow. And when they emit their light and they get to a place where they can cool off enough such that they emit light, that's when we see the light coming from the granule. But because it's a hot gas, if it emits light, then it cools off. If it cools off, then it'll sink because a convective flow, you have hot gas rising and cool gas sinking. So each one of those little nodules is actually the center of an upwelling flow, and the dark places between them are where the hot gas has cooled off and now it's sinking back down. And the reason it's redder as opposed to yellow is because it's cooler. And so it has emitted its light, it's emitted its heat to space above in the solar atmosphere above it, and then it is now cooling off and sinking. So these things can be very, very, very large. These granules can be up to the size of a continent. They can be about 1,000 kilometers across. And so they move around and they provide the base of the photosphere. And basically the granulation that we see here, those are the things that basically are what we call the photosphere. So the granulation of the photosphere is it. So granules are therefore pretty small features, and pretty small is 1,000 kilometers or about 600 miles across. And they cover the entire surface of the sun except where sunspots exhibit. But remember something, but each individual granule lives for only about 20 minutes or so. So you have this structure on the sun that's hundreds of miles across, 600 to 1,200 or 1,000 miles across, about 1,000 kilometers across, that rises up, emits its light, cools off, and then descends back to the sun. So this is an enormous, enormous roiling, windy place because it's called gaseous. So you can think of these as upward welling winds, and that's a really good way of thinking about it. So the flow in the granules can be extraordinarily fast, and many miles per second, about 15,000 miles an hour. And they actually, because of that, will produce sonic booms at the surface. So there would be interesting waves that get produced because of how fast they move. And so they themselves will create waves of basically pressure waves, and those would be sonic booms. So these things are moving faster than the speed of sound, which is really interesting. Something about the size of a continent, a gaseous cloud, moving almost that's about the size of North America or larger, moves up or down at faster than the speed of sound. Really interesting. Okay, but then you can actually look at much larger structures, and these granules can be grouped into what are called supergranules, and they can be much larger than the Earth, and about 35,000 kilometers across, which is bigger than the Earth by a factor of say 4 or so. So 4 or 5 times the size of the Earth, and we see these large, large, large structures, and they're called supergranules. And so we can think of them as a basic huge bubble upon which the minor granules flow. So there's bubbles on top of bubbles on top of bubbles, or more specifically, bubbles of bubbles. And so a supergranule is a bubble of bubbles. They tend to be much slower moving, but they also are gradually evolving too. So it's kind of a scale sort of issue, and we notice them by looking at a Dopplergram. And so this particular sub-image is a Dopplergram that shows the speed, basically the emitted light at one wavelength. And if it's brighter, it's moving towards us. If it's darker, it's moving away from us. And so you get a Dopplerogram of these large objects. And since this is the entire disk of the sun, we're seeing very, very, very large features that are bigger than the Earth. And so these large wave-like structures have granules inside of them, and then they move up, emit all their light, and then flow back down as a unit. So that's the granulation and sunspots of the photosphere, but they deposit their energy to another layer that's just above the photosphere that we call the chromosphere. And the chromosphere is cooler, as a cooler atmospheric atmosphere above the solar photosphere. And the chromosphere can only be seen when there is a total solar eclipse, or you have some sort of spacecraft that it can block the light of the sun very accurately, and so that you can actually visualize the chromosphere. But the chromosphere extends above the photosphere. It is cooler, but still extraordinarily hot. And since it's hot, it will glow with this characteristic pink glow. And that characteristic pink glow is that of hydrogen. And that's what you're seeing in this image that Dr. Reddy did of the total solar eclipse back in fall of 2000, August of 2017. You can't even see it unless the moon covers it during an eclipse. But you can see other things there too. We're not talking about the white sort of puffiness that's going around about it. That's part of the corona of the sun. I'm more specifically talking about that pink glow right at the rim of the moon, and not the pink glow that's off to the right-hand side. That's a prominence. I'm talking about that lightish pinkish glow that's all around it. That's the chromosphere, and it's chromos because it's a color sphere, and the color is pink. And the chromosphere is heated in these spiky storms called spicules, and we see them. These observations are observed by NASA's Solar Dynamics Observatory, the SDO, and we can see them near the North Pole. And so SDO gets a full view, and it's looking at ultraviolet, so we can see where the spicules are, and the spicules form. At high definition or high resolution, we can see that the chromosphere is primarily these spicules plus a dim glow right above. So the spicules are kind of like these upward shooting jets, and they change radically and over extraordinarily short periods of time. So we can think of them as almost vertically pointing tornadoes of hot gas, which is a good way of thinking about it. And those are spicules in the chromosphere. The next surface feature that we see are called prominences. And they're called prominences because, well, they're prominent. And they tend to be looping structures that lift above the sun and carry tens of billions of tons of mass of material with them. So this is an example of the sun, I believe, that was taken by NASA. And this is amazing, amazing loop prominence that's extraordinarily large. Underneath that loop, hundreds of Earths could fit. It's a huge, huge, huge loop. All right, here's another example of an interesting prominence that was taken by the Stereo spacecraft, or I believe the Stereo or SOHO spacecraft, another NASA image. And it's basically a lifting gaseous bubble and loop that's coming off of the surface of the sun, and they're called prominences. And now we're going to look at it. I'm going to go and show you a couple of interesting prominences to show you how they move. And this series I'm going to show you in just a second. These prominences can be extraordinarily large, and they're guided by the magnetic field of the sun. So charged particles get in the magnetic field of the sun, they're lifted off the magnetic field of the sun, and they move as the magnetic field moves in the sun, and it's very dynamic and fluid. And as it does so, the charged particles flow on the magnetic field, and you get these kind of filamentary appearances to them as the charged particles fly along them at an extraordinarily fast pace. And I put the Earth in there just to help you see the approximate size scale of some of these things. Now we can see a video of that same loop that was taken in March 30 of 2010. And that was very short after the Solar Dynamics Observatory actually opened its mirror. And what we're looking at here is the change of the prominence over the course of a few hours. The Solar Dynamics Observatory takes pictures every 10 seconds of a particular wavelength, and so we can see how the prominence itself moves over time. And you can see the action of the spicules in the background. So don't just look at the prominence that's occurring there. We see that the spicules in the side areas are actually little shooting jets type of spikiness, and that's just by the words in the image, and also at the limb of the sun. And when I say limb, I again mean what you call the edge. So look again as it zooms out, we see a series of spiky features, and those are called spicules, and the glow right above it, that would be the chromosphere, and the prominences are above that. Prominences tend to happen around sunspots, so there's a link between these active regions, which are the glowing region that you see there, and this is of course taken in extreme ultraviolet light. But if we were to look in that area in visible light, maybe say just normal light that we would see with our eyes, we would see a dark sunspot. So there's a difference in the view that we have of the sun when we look in ultraviolet as opposed to visible light. Next thing we're going to look at is what's called the solar corona, and this was by Stan Honda. Stan Honda also went out to see the total solar eclipse, and he made sure that he got some beautiful, beautiful, beautiful images of the eclipse. And the corona is the gaseous material that comes off of the sun and streams out into space. So strictly speaking, the sun doesn't really have a solid surface, because where does it end? It really doesn't end. The solar corona is an extension of the sun. The photosphere is where most of the light that we see comes from, but the corona is only visible when the photosphere and chromosphere are both blocked. So you need a total solar eclipse in order to see it. And if you go to see a total solar eclipse, yes, you actually do see this in the sky. It's absolutely fantastic and gorgeous. But the corona itself is also rapidly changing and guided by the magnetic field, and is a product of the magnetic field of the sun. In fact, if we look at this thing on the right, we see that it has this kind of leaf sort of structure on the one that's pointing at 2 o'clock. We see it's kind of broad in the side, and then it kind of pinches at the top. And that's kind of very common for appearances with the corona. Well, if we actually take a spectral analysis of the chromosphere and the photosphere, we can determine the materials that make up the sun's atmosphere. And this is a sample sort of thing that we might see. But if we were to actually go to the McNath Solar Observatory, which is down in Tucson, Arizona by the border, right at Kitt Peak, we find that a high resolution solar spectrum shows enormous, enormous, enormous numbers of spectral features. And simply by looking at all of these spectral features and taking out what we call telluric lines, which are absorption features due to the Earth's atmosphere, we can determine we can observe in the solar abundances and what exactly makes up the sun. And when we do that, we actually discovered that the sun's atmosphere is about 90% by atomic number, about 90% hydrogen, and by number about 9% helium, with very, very, very trace elements of everything else. So the action of all of those things is mostly because the sun's mostly hydrogen and helium, and all of the other lines that you see come from extraordinarily trace amounts of the rest of the elements. So the solar atmosphere itself, if we look at the entire thing, it starts at the photosphere at about 6,000 Kelvin. The chromosphere is when it gets cooler. It transitions then into the corona, which then is another 10,000 kilometers up, or about 2 Earth diameters up, or about 2 Earth radii up. And then we get out into space, and it heats up enormously. It gets up to millions of Kelvin. So the corona itself is extraordinarily hot gas. It's very, very, very tenuous and visible in X-rays because of the temperature. But it's interesting that it actually has this temperature profile, and the study of this and why it cools down for the chromosphere and why the corona then gets so much hotter. That's an area of active research. So occasionally we don't see these things. This is a view of the quiet sun when there's no sunspot activity and no prominences and everything like that. And that's all interesting and everything. And this is where looking at the sun in visible light. So we see invisible light at a specific wavelength of 6562.8 angstroms, which is in the red region of the sun. We see that the sun has that mottled appearance of the granulation, and we see a couple of tiny sunspots and very few spicules and very modest prominences. But this is what we would call a sun that has very, very, very quiet appearance to it. And sometimes we have magnetic fields and sunspots. So let's look at that in more detail. So how does the magnetic field of the sun create a sunspot? Well, the magnetic field is generated deep inside the sun, and occasionally the magnetic field bursts through the surface. And when it does so, it's doing to try to release energy. And so the magnetic field becomes tangled inside the sun as there's rivers of current, literally current rivers of electrons flowing very quickly in a literal current inside the sun. And that creates a magnetic field as a dynamo effect because of the differential rotation of the sun. So the magnetic fields get set up. And occasionally the magnetic fields bunch up inside of the sun and therefore poke through the surface. And when they do, the magnetic field lines, they have a direction to them. And the north end of the magnetic field and the south end of the magnetic field, where they puncture or at least go through the photosphere, that's where sunspots occur. So where the magnetic fields come through or breach the photosphere, they cool off the surrounding photosphere by giving a way for the particles to remove their energy. So they can flow along the magnetic field lines, and as they do so, they can emit energy and therefore cool off. Therefore, the sunspots are places where it's cooler. And so that's why you also get them in pairs. Why you have sunspot pairs is because they trace the magnetic field of the sun. So the magnetic field traps the gas and then allows the sunspots to be cooler and deep inside the convection cells, because remember there's this roiling convection that's happening under the sun, and so we have all this motion of hot, hot, hot gas, which is essentially what we call a plasma, and a plasma is an ionized gas. And so if you have motion of an ionized gas, you're going to create electric fields, and electric fields in motion create magnetic fields. And so it's an incredibly complex interplay, which creates magnetic fields that then burst through, and that's the only way that they can go is that the magnetic field itself creates a loop. And then that magnetic field is invisible unless it has hot gases in it. And then those hot gases then can emit light in order to cool off as they move through the magnetic field. And that's what we're seeing here, is that as the hot gases move through the magnetic field, they cool off, and as they cool off, they emit light, and that traces the magnetic field. And so they aren't solid objects, and they're not things. Those are just filaments or rivers of hot gas that are charged particles that are flowing through these magnetic fields. All right, so now what's interesting is as the sun rotates differentially, there are times when the sun has a very even magnetic field, and then over time, the magnetic field is tied to the gas inside it, but the sun rotates differentially and so drags the magnetic field around and really tangles the magnetic field up. So occasionally you have magnetic field lines that then get parallel to each other, and as they do so, there's a pressure that happens between one magnetic field next to another, and in order to relieve that pressure, they poke through the surface to create those sunspot pairs. And that's what we're seeing here, a nice quiet sun where the magnetic field is all nice and regular. And then as the uneven rotation rate of the sun, slower at the poles and faster at the equator, tangles the magnetic field, eventually gets so tangled and all the magnetic fields get so close together that it's much easier to release that energy by bursting up and getting out of each other's way. In just the same way, when you have like toy little magnets, they really kind of jump away from each other when you push them together and want to go to a more even state or a more lined up state. And so this is the attempt of the gases in the magnetic field to kind of make a more lined up state. But there's incredible energy associated with it, and they can't do it, so the first thing they do is create a sunspot. So that means that solar activity changes with time, and you can go from quiet times to active times, back to quiet times, back to active times. So we have the solar activity changes with time, and how many sunspots there are changes. And if we look, we'll find that we can actually hunt for this throughout history. When Galileo first started looking through a telescope, one of the things he did was to stare at the sun. And you shouldn't do that, but he was drawing things and he didn't know. But it was very, very bright. But he did his own drawings of the sun and saw sunspots. And if you make an image, make a little movie out of the sunspots that he saw, then you actually see that there's 36 plus drawings, there's 36 drawings that he did, shows that these sunspots move across the surface. Well, we don't see those sunspots today, we see different ones. And in fact, the sunspots that he drew changed from day to day. The sun has a cycle that every 11 years, the sunspots begin at higher latitudes and then get more and more and more concentrated. There's more of them, and they go to lower and lower latitudes, closer and closer to the equator. So as a sunspot cycle occurs, you start from very few sunspots, then a few appear way at high latitudes, then more appear at lower latitudes, and they get closer and closer to the equator, and there's more and more and more of them, and then all of a sudden they all dissipate. And then you start again. So you can count, the solar cycle is a counting of sunspots, and this has been done for a very, very long time. And this is what I mean by that counting set. We can determine how you want to count them. It's like how big they are, how small they are, where you see them, and so forth. But if we see as time progresses, that this 11-year cycle shows that sunspots for a very short period of time. We have a solar minimum, which is the minimum number of sunspots. Then you have a solar maximum, where there's a maximum number of sunspots. And then all of a sudden they go to the equator and then dissipate rapidly, and we get a minimum again. So this is the solar cycle. And in fact, it's actually a 22-year cycle because we switch magnetic polarities. It goes from magnetic north to magnetic south and so on. And therefore, the number of sunspots is every 11 years, but if you add in the magnetic polarity, it's every 22 years. And then there was an interesting time right after Galileo started looking called the Maunder Minimum, where there were few, if any, sunspots. And it was not for want of looking, because people really were looking for them at that time. We'll get back to that in just a second. The solar cycle has been observed for an extraordinarily long time. We can see from here, from David Hathaway's work at NASA, that the sunspots are summarizing all the total number of sunspots throughout history. And he started his work looking at the historical place from 1750 and onward. And we can see there's been a number of sunspot cycles. And these are good counts of people looking at the sunspots for a long period of time. And if we then go back all the way to using Galileo's data and start from 1612, we see that sunspot counts have been fairly consistent, that this cycle has been consistent roughly since the year 1750. But there was a time, roughly around 1650 to roughly 1700, that's called the Maunder Minimum, where there were no sunspots. People were counting and were looking for them, but saw none. And it actually corresponded to a time of cooling on the northern hemisphere. It's interesting that would occur, but nobody really understands the nature of why that would occur and what the point of that is, or if there's any meaning to it. But understanding what the Maunder Minimum did and how it actually influenced our climate on Earth for those 50 years, it's a fascinating study. So decadal-long cycles in the sun actually do have influence on the sun, on the Earth. And so the solar cycle affects us here. Next is some very interesting stuff. There's solar flares. Sometimes on the surface of the sun, on the photosphere, you get extraordinarily violent events where active regions, like this massive sunspot region that's smack in the middle of the disk of the sun, there's some really, really, really huge, massive active regions. And we call them active regions because there's going to be flares, there's going to be prominences, there's sunspots. They're called active regions. And solar flares can be graded from various types, but one of the largest types are called X-class solar flares. And though if it's a logarithmic scale, and so if you have an X-type 10 or an X-type 17, it's an extraordinarily large output. And so what happens in a solar flare is the following. We can see that in this particular thing, that was the image from then, and these are the satellite images that were taken by the SOHO spacecraft in 2003. The green image in the upper left shows the visible light image, or at least an ultraviolet light image of the sun. It's an ultraviolet light image that shows the solar flare occurring, and the solar flare is a momentary brightness, or some brightness that occurs over the course of a few minutes. And it's enormously large areas. The total energy output that can occur in a solar flare, you can see up in the green, which is in the ultraviolet, it will be on the order of tens of billions of nuclear bombs, 100 megaton nuclear bombs, all at once over the size of an area much larger than the Earth. So you can think of it as one of the incredible large output of energy. And because of that, you get X-ray emission and you get gamma ray emission, and there's the temperature on those areas in the sun can reach 10 to 20 million Kelvin, which is actually hotter than the center of the sun, and you get nuclear reactions on the surface of the sun. So that's what's happening with the solar flare event that you're seeing in the green. Then the result of that is which is shown in the red and blue, which you see after the solar flare occurs. We see the corona in the background, which is kind of this constant sort of flaring out on the sides. But then you get this burst that occurs. When the flare happened, it emitted an enormous amount of material, and might be hundreds of billions of tons of mass that flowed out at nearly the speed of light out from the sun. And it gets to Earth in a couple of days later. And when it gets to the Earth a couple of days later, you get events, or even hours later, depending on how fast it's going, which can actually cause the sparkling that you see in the in the telescopes of the SOHO spacecraft. So we see a continual outflow, which is called the solar wind. We see the corona, which is the constant streamers that are coming out. And then we see the coronal mass ejection that was directed straight at Earth on that date. That caused a power outage in 2003. And now I'm going to use a NASA video, which is a really interesting video that shows a prominence and an eruption of a coronal mass ejection back in 2013. And we see the prominence that occurred on the limb of the sun, and there's the prominence occurring. You can see the spicules and the granulation on the surface of the sun, and we see the flaring contrast. But as the sun is emitting this material, it also had a flare. So the Solar Dynamics Observatory could only see the prominence and the flare occurring, but the rest of the imaging was taken by, of course, the SOHO spacecraft, as well as the stereo spacecraft, which are also orbiting the sun. So the Solar Dynamics Observatory takes a small amount, and there you can see the link between the prominence and the SOHO spacecraft's observation of the coronal mass ejection that came off of the sun after the prominence occurred. So it released materials deep into space on May of 2013, and now the SOHO spacecraft has a much broader field of view, and we can see the coronal mass ejection going out into space. And that's hundreds of billions of tons of material. The other stereo spacecraft, which is away from it's trailing the Earth in an orbit, so it gets a different vantage point, about a quarter of the way around the sun. And we can see the coronal mass ejection from a different vantage point as it trails the Earth about a quarter of the way around. And we're looking at the extreme ultraviolet. And now we go to the green view, which is another view by stereo. And this is what's called, the COR stands for coronagraph, so it's covering the surface of the sun. And now we can see the coronal mass ejection from another coronagraph. So the coronal mass ejections can influence the Earth massively, and they come from these active regions of the sun. Oh, and if you want to go see these things, go look up the Goddard Space Flight Center at NASA. Their visualization stuff is fantastic. So we see a link between prominences and coronal mass ejections. So what can we have as a problem with this? The largest solar flare known to ever happened in September 1st of 1859. And when the coronal mass ejection reached Earth, it actually wiped out the Earth's magnetic field. It was the largest possible solar flare that's been known to have ever occurred in the history of observing the sun. After this solar flare occurred that Richard Carrington saw on September 1st of 1859, the next day, the aurora was visible all across the Earth down to the equator. And normally it's only in high latitudes, way, 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 way north. But basically it erased the sun's magnetic field, and the telegraph had recently been invented, and people could actually broadcast telegraph messages across the United States without the batteries, because the batteries themselves were blowing up. So they couldn't actually use telegraphs with the batteries. They didn't need to. The ground was charged, and so there was an enormous charge across transatlantic cabling. If a Carrington-class solar flare occurred today, we would have massive problems here on Earth, unless, of course, we chose to do a huge power outage across the entire United States in order to preserve our electronic infrastructure. And you should really know that everybody who does any kind of work inside the electrical industry knows what a Carrington-class solar flare is, and they watch spaceweather.com in order to understand this stuff. And the solar wind is therefore the particles that come off of the sun. Usually it's huge amounts of material, but for a very, very, very short period of time, a coronal mass ejection can have an enormous influence on the surface of the sun. But we can see from this graphic that actually what's happening is which is from NASA, is that the particles are being redirected. And why are they being redirected in general? Because the Earth has a magnetic field. And so here is a schematic of kind of the interaction of an active sun creating a solar flare that has a prominence that's visible to it. That prominence, that activity creates a coronal mass ejection that then travels out into space, and if it happens to interact with the Earth, some of those particles go down into the Earth's magnetosphere, which is the blue area that we see in the upper right, and can give us aurorae and amazing geomagnetic storms. So the Earth's magnetic field protects us. It protects us from the solar wind, and it protects us. But the coronal mass ejections can actually plow through and wipe out the Earth's magnetic field for a brief period of time, allowing the particles to reach the Earth and form the aurorae that it can happen in like a Carrington-class solar flare. So without the Earth's magnetic field, we wouldn't be here. We wouldn't have modern technology. We have grown up in a time where modern technology is protected by the Earth's magnetic field. And so spacecraft that live outside the Earth's magnetic field have to deal with that. And some spacecraft have been destroyed. Not all. Thousands of spacecraft are up there, but only a handful have ever been truly wiped out by it. But if there's going to be a Carrington-class solar flare, every plane's going to be grounded. We'll probably have massive brownouts or power outages just so that the equipment doesn't get damaged, if that ever occurs. And so what's really beautiful is that the source of the aurorae, and this is a view from the International Space Station, as the solar wind passes through the Earth's magnetic field, it spirals along our magnetic field, just like the particles spiral through the magnetic field of the sun. They can spiral through the Earth's magnetic field, and as they bounce around the Earth's magnetic field, as they hit the Earth's upper atmosphere, they cause the glow in the sky that's called the aurorae. And it's a beautiful thing to see from the ground, but it's really fascinating to see from the International Space Station like this. And here's what solar flares can do. They can damage spacecraft. They can cause the Earth's atmosphere to heat up and expand, and therefore actually cause drag on satellites and cause them to come down. It actually can harm satellites. We saw in the solar flare that there was all those sparkles. Those are protons that are coming at nearly the speed of light and can damage the electronics of a spacecraft. And it can also create currents in the ionosphere, which is which basically can disrupt GPS signals. It can disrupt radio transmissions. It can also influence aircraft satellites as well. There's all sorts of crazy things that can happen. If there's cables underneath the ocean, you can have incredible ground effects from there. You can have currents in pipelines. So yeah, the sun can do things to pipelines underneath the ocean. It's amazing. So knowing space weather is kind of critical to modern society. So that's why it's done. That's why NASA has this fleet of spacecraft to understand the sun. So the solar wind mostly escapes through the coronal holes where you have where the magnetic field, where you see the loops and flares of the corona, but you see these streamers coming out. Those are the coronal holes where it's cooling from there and material is flying away. And the coronal holes can be seen because they're darker in X-rays, as the sun looks bright in X-rays, and the coronal holes are where the solar wind arises. And as the field lines loop back to the Earth, they're trapped. But if the field lines extend out into the outer solar system and out in interplanetary space, then you get those beautiful, beautiful coronal features. And then that's the origin of the solar wind. And the particles can go out, meaning mostly protons and electrons, accelerated to extraordinarily high speeds and can reach the Earth in a couple of days from 93 million miles away. So that's pretty much it about the surface appearance of the sun. So I invite you to take a look at some of these questions about the sun's appearance. Go take a look at it, and we'll see you soon.